All right, good afternoon, everyone, and welcome to the Washington Statistical Society virtual seminar. My name is Katherine Irimata, and I'm the current WSS Methodology Program Chair. Today with Ching Pan, I'll be chairing today's presentation. So we'll be hearing a talk on a regression tree approach to missing data and sample surveys from Dr. Wei-Yin Lo. And then afterwards, we'll have time for questions and discussion. If you have questions during the presentation, please submit them in the chat, or at the end of the presentation, you're welcome to ask any questions by raising your hand. I'm pleased to introduce our speaker today, Dr. Wei-Yin Lo. Wei-Yin is a professor of statistics at the University of Wisconsin-Madison. He has a PhD in statistics from the University of California, Berkeley, and is a fellow of the American Statistical Association and the Institute of Mathematical Statistics. He has held visiting fellowships at ABBA, the Bureau of Labor Statistics, and IBM Research. And he's also consulted for some major biopharma companies. Professor Lo has been researching classification and regression tree algorithms and their properties for almost 40 years, and he's the author of the guide algorithm and software. So I'll now turn it over to you, Wei-Yin.
Thank you, Katherine. Okay, so I was approached by the USDA Economic Research Service about 2 years ago on using regression trees to do missing data imputation. So, so today I'm going to talk about what I and my colleagues at the ERS have accomplished so far. So this is still ongoing work, and I guess I should have this usual disclaimer that none of this represents the USDA, and it's all my opinion. So in the abstract of the talk, I said I was going to go over 3 examples, but when I made up the slides, I realized I would never have time to do all 3. So I'll just mostly spend my time on the USDA example. And at the end, I want to show you a rather surprising example involving COVID-19. So the USDA has this ARMS survey, Agricultural Resource Management Survey, that I think annually is carried out, and they survey all the farm operators in the United States to anticipate trends and emerging issues in agriculture, food, environment, and rural America, and they produce estimates and forecasts of incomes. So what they would like to do, what they have been doing, is to try to estimate the total farm household incomes and expenditure. Okay, so this slide tells you a little bit more about the data. So the data set I was given to analyze was last 2 years ago, 2022. There are 18,188 records. These are farms, and the whole survey has more than 800 variables. But because they were particularly interested in these 3 totals at the bottom of this slide, which involve income and expenditures, they decided to narrow the number of variables to 76. And these are variables that would be helpful to estimate the total farm income, total household expenditures, and total farm assets. All right. So each of these is a total of 10 variables that were collected. So the totals were not collected from the survey. They're supposed to calculate the totals from the surveys. But the problem is some of these components have missing values. So what currently the Economic Research Service, ERS, does is that if all the components are available, they would calculate the total. If one or more of the components is missing, they will not calculate the total. So as a result, you get missing values in these totals. About 50% of the respondents do not have the totals because one or more of the components is missing. And so they try to impute the missing values, the missing totals, but they don't use the components that are non-missing. So there's a great loss of data that are not used. All right. So this gives you some idea about the variables. There's some farm variables like size of the farm, total amount of financial assets, total cash expenses, type of farm, number of household members, and so forth. So these variables have no missing values. And then the operator variables like marital status, age of operator, educational class, gender, and so forth, and they have no missing values. Well, the other variables are the income, debt, and so forth. And the interesting thing about this data set is that, so let me just jump ahead to say like household income, okay? The first variable, R939, household income from private pensions and private disability payments. So these should be dollars, but in the survey, they don't record the actual number of dollars. They just indicate a code. If there's no value, no such income, the value, if the value is 0, the code is a 1. If the amount of income for that variable is between 1 to 500, is coded 2. So so you don't know what is actual dollar value. All you know is this bracket range. And a very interesting thing is that 0 does not mean 0. If the code is a 0, then it means do not impute. All right. So if a question is irrelevant for whatever reason, then it is coded 0. And if it's a value to be imputed, it is coded -1. All right. So you can see that there could also be negative values. So if it's an income and if it's a loss, then say if the loss is between if it's a loss of between 7.5 thousand to 10,000, then it will be coded a -9. So the range of these codes go from -34 to 34, right? With the exception that there's a 0 and there's a -1, which are special, right? So when we impute, we have to be careful that we don't impute a 0, because if it's $0, it will be coded as 1. So a 0 means don't impute. For a good example, as we'll see later, is age of spouse, right? So if age of spouse is missing and the person is not married, that will be coded as a 0. But if the age of spouse is, if the person is married, the person doesn't want to tell you the age of spouse, then it's a -1. Right. So, yeah, okay. So these are all the variables, some of the variables, and tell you the number of missing values. So for example, R39, 939, 33% of the data have -1 as a code, which means that you need to impute them if you want to get a complete data set on R939. R951, the number 951 and so forth refers to the questionnaire, the question in the questionnaire. So the number item 951. Spouses off-farm wages, salaries, and tips. 15 of them, 15% are negative ones, which for some reason the farmer does not want to reveal. But 24% of them are 0. So this 24%, so you can see here, these are all related to spouse. These are people without spouses, right? And then there are also sometimes like conditional questions like here, value of producer's dwelling if not owned by operation. 22 of them should have an answer, 22%, sorry, should have an answer, but they are not provided by the respondent. 55% are coded 0, which means that this thing about if not owned by operation, I assume that 55% of these producers, the word producer and operator are used interchangeably. I think 55%, a little bit more than half of the respondents, their dwelling is owned by the operation. So that's why they are not, you should not impute them because they are not relevant to this question. So here are the compositions of those 3 variables, the totals. The first one is total off-farm income, and it's made up of this, I think, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 components, but 50% of the data are missing this because of one or more missing component. Total household expenditures, the next one has got 54% missing because of one or more missing components. And then the last one is total off-farm assets, NFASST, and 48% of them are missing. So these are the things that are imputed by ERS. And I put it highlighted in yellow at the bottom. These equations are meant to be used by, first of all, converting the code ranges, those integers, into dollars, and then you add them up, right? So it obviously does not make sense to add up the integer codes. So what they do is they take the midpoint. So for example, if a value, let me clean this up. So if a value is 10, if a value is 10, if the value of that variable is 10, then you convert it to dollars to be the midpoint of this range, which is $12.5 thousand, right? So that's how one would use these formulas. And these are the components. So for total off-farm income, that is income from private pensions, total off-farm wages, salaries, total net cash income from operating any other business, dividend income, interest incomes, and so forth, right? And they could be negative if there was a loss. So like gain or loss, it could be negative. And the numbers in parentheses beside each line show the missing values of each of these components. This is the total expenditure. So the rent payments, amount they spend on food away from home, utilities, and so forth. And again, the percentages beside each row, at the end of each row, show the missing percentages. And there are 12 of these components for expenditures. And then the non-farm assets, the value of financial assets held in non-retirement accounts, value in retirement accounts, value of household vehicles, and so forth. And again, there are lots of missingness in all of this, right? So what does the ERS currently do? So what they do is that they will take each of these variables and try to impute them. The way they impute them is, so if you have a farm which is missing one of these, say total off-farm expenditure, the first one, they will find out for this farm what is the age, class, and education class of that farmer. These two variables are non-missing, so you can always find them. And if you find that that person belongs to this class, then you will impute the missing value of that total with the mean of the totals for all the people in the data for which you have that observation, right? So this is called conditional means. The condition in the class, you just replace with the mean, okay? And people in the ERS feel that this is not very efficient, but they have been doing this all the time, all the years, and they weren't sure what to do. So the observed values in the components are never used. Okay, so there was a feeling that there's a lot of wastage of information. So let me just briefly talk about how people normally do missing value imputation. The first is the regression approach. So you usually fit a linear regression to the responses, and then use a model to get the predicted values. And if you want conditional mean, you can use that regression model to predict the values to impute, or you can perturb it a little bit to add some noise. Then there's of course the hot bag method, which is you partition the sample space into imputation cells, and then you impute missing values by random sampling of responses within the cells, right? So here's just a two simple graphs to show you the standard method using linear regression and the regression tree method, which I'm going to talk about later. So on the left side, we have a y variable with some missing values, and then we have an x variable, and we assume the x does not have missing values. So we want to impute the missing values for y. So we can plot the y versus the x for the non-missing values only. Otherwise, because you cannot plot the missing values if y is missing. So you plot the missing value, non-missing values on the left-hand side, and it looks straight, so you fit a straight line. And if there is a So if there's somebody, say, with an X here, and you want to impute, and that person is missing Y, you just go up here, and then you impute that, right? So that would be sort of like conditional mean. You use the mean of the linear regression, all right? So that would be one way of doing regression imputation. It assumes that you have a correctly specified model, right? It assumes that the straight line is correct. And that's the most difficult thing with traditional methods, is to get the model correct. But it also assumes that the missing and non-missing data follow the same distributions. Otherwise, you can use what you see in the non-missing data to predict what's happening in the missing data. So now you could also do hot deck imputation. So the way you do hot deck imputation is you take the range of Y from this linear regression model, and you just maybe here I just cut it into the quartiles, right? So 25% above the first line, next 25%, and so forth. And where they meet the regression line, you have these vertical lines. I'm not drawing this very well because I'm trying to like drawing on a wall here with my iPad. So now if you have a person who is missing Y, but whose X is here, then this is the imputation cell for this person, right? So here, this induces 4 imputation cells, right? So then if you want to do hot deck, you will take one of these observed values of Y and randomly pick one and impute it for the missing value for that person with an X. On the right side is the same picture, the same data. If you see carefully, the same dots, but I use a regression tree. So the regression tree, what a regression tree does is trying to estimate that straight line with a step function, right? So it's an algorithm, people call it a machine learning method, that will approximate this, try to approximate this regression line on the left with a step function, which is the rate steps. And because it's a step function, you automatically get the imputation classes, right? Where the steps jump. So here I have 5 imputation classes, and the same thing. If I have an X here, right, and I want to impute the Y, I could use the red line for this imputation class to do a conditional mean imputation, which will be a constant for every observation that is missing Y but whose X is in that imputation class. Or I can do hot deck by randomly selecting one of these points, right? So one advantage of this regression tree model is that it overcomes this critical assumption that the model is correctly specified, because there's theory, asymptotic theory, that says regression tree models are asymptotically consistent regardless of the shape of the regression line, the true function. So of course, if the true function is a straight line as on the left, you will see that this regression tree is not a very good approximation. But if it's anywhere not a straight line, then the linear regression method will not work. So here's an example where actually the data follow a parabola kind of shape, and suppose you don't know you fit a straight line, right? You can still do all the imputation and so forth, but they will not be very accurate. Whereas if you look at the right side, the regression line, that step function is coming down and going up as it should, following a parabola, right? So one good thing about a regression tree method is you don't have to worry about model misspecification, right? It will do its best to fit the whatever unknown curve. But going back to here, if you look at this, you'll say, well, then why is the regression tree, right? You don't need a tree, which is true. I mean, this picture on the right with the so-called regression tree model is just a way to approximate that straight line with a step function. You don't need a tree. Well, where the tree model is good is that this picture that I've been showing you can be represented as a decision tree. So here at this point, here, So at this point, this is the first cut. This is 13.7, right? So this goes to the left. So 357 is the height of this red line. Okay, so you can visualize this graph on the left with a decision tree function. Okay, it tells you exactly where the boundaries of the imputation cells are and what are the heights of the red line. Of course, you don't need this tree diagram because everything is already clear from the left-hand side. Well, until you have more than one x variable. If you have more than one x variable, and if the imputation cells use two or more x variables, you will never see the picture on the left. But the picture on the right can always be shown, right? So, for example, I may split, the first split here may be x1. The second split here may be x5. This split may be x11, right? So even when you cannot see the graph, you cannot see the data, you can still understand the tree. So that's the other advantage of a regression tree, is that when you have high dimension or even low dimension, anything beyond one dimension, it works very well. Besides, the regression tree does automatic variable selection, right? So it determines at each point whether it should be x1 or x5 or x2 and so forth. I won't have time to talk about it in this talk, but that's what the regression tree can do. The other way is to use propensity scores for hot-deck, right? We all know the standard thing, the way to do to find imputation classes is to get estimated propensity scores and use the propensity scores to induce your imputation cells. So on the left-hand side, I have the usual logistic regression model, and I'm plotting a logistic regression curve, that red S curve, to estimate the probability that Y is not missing, right? So imagine Y is one of those totals we're trying to impute. Now, unlike the graphs I've been showing you, where I can only show the points where X and Y are both observed, here I use all the data because the observed Y are represented by sort of the indicator Y is not missing, and the unobserved Y are here, right? Y is 1 if, sorry, the value is 1 up there if Y is non-missing, and if Y is missing, then you have the dots at the bottom. So that's how you fit the logistic regression. So for logistic regression, we use all the data, although we don't use the actual values, but we use all the data, whether missing or not, they're coded as 1 or 0. All right. So let me clean this. All right. So the usual way of doing hot-deck imputation with propensity scores is we fit this S curve, and then we cut up the y-axis into with horizontal lines. Here I cut it up into 5 equal parts. And so, for example, here this will be 1 imputation cell. Sorry, not imputation. This is 1 1/5, 1/5, 1/5, right? So if we are in this fifth, then you draw this line to where it meets that, and then you project down, and then you have 1 imputation cell here. Okay, so this imputation cell corresponds, the X values in this imputation cell corresponds to all those observations that whose probability of Y being non-missing is approximately between 0.6 and 0.8, right? So that's how you create the imputation cells with logistic regression. On the right-hand side, I have the same data exactly as on the left-hand side. You look at those light blue points, they're exactly the same, but I fit a staircase again. I don't fit an S curve, right? Because you with logistic regression, you need to make sure that your logistic regression model is properly specified, right? And you never know because you cannot really see in high dimensions. It requires a missing at random assumption as usual. Okay, so the right-hand side, just a very simple 3-step function, and it's trying to approximate in a very poor way the S curve. And because there are only 3 steps, we only have 3 imputation cells, right? So in this one imputation cell, we have a lot of non-missing data. and only looks like only 2 observations are non-missing, are missing, right? The ones are the ones that non-missing. So for these two for these two fellas for which you don't know the Y, we know that X is in this imputation cell. We would randomly pick one of these guys to impute, okay, because we know their Y values. Over here on this imputation class, we have a lot of missing values and we have fewer non-missing, but still substantial number. So to impute all the missing values in this first imputation class, and there are many to be imputed, we would randomly draw from those at the top, right? And again, you can draw it as a tree. So this picture is the same picture as what I showed you on the left, on the previous slide here on the right. So I just reproduce it, and now you go draw a tree. So the same story. You can have a decision tree to show, especially helpful if it's in high dimensions. And also you can actually see explicitly what are the boundaries of the imputation classes. Now, what happens if some of the X variables are missing? Okay, so I draw these pictures with X as the predictor variable, but X actually is usually a linear combination, right? Like here in linear regression, right? So X is not a univariate, it's not a single variable, maybe multiple linear. So I call them Z. So if Z's are the variables they are predicting, and if one of the Z's is missing, you cannot use that observation. So even if you think the logistic regression model should be approximately correct, if you have a lot of missing values, excuse me, in your predictor variable Z, you can't really fit that model, right? Whereas with the logistic with the regression tree, I'll show you what happens if some of these X values are missing pretty soon. Okay, well, I'll show you now, right? So in the regression tree, so back to here, right? So the first split is when you split the whole data, right? Here is 18.54, happens to be this split, I think. It's about 18.54. So you split on left and right. On the left, you don't split anymore. On the right, you split again. So what it does is that it looks for splits like that, X less than or equal to a constant C, and it does a sweep of all the C values to find the best cut using some criterion. And in this case, the constant is 18.54, right? So this is what happens if you do not have missing values, right? So and if X is the variable chosen to split a node, it does a sweep on lowercase x. Lowercase x was the C I wrote earlier, right? Now, but on the other hand, if X has a missing value, and suppose there's only one missing value, okay? Later on, we'll talk about multiple missing value codes. If there's only one, then the guide will look for 3 types, will find the best of 3 types of splits. The first split is X equals to NA, and NA here is just a convenient a code for missing values following R, right? So it says, oh, I forgot to say, at every node here, there is a condition. If the condition is affirmative, if it's satisfied, then you go to the left. Otherwise, you go to the right. Okay, that's why I put the condition on the left, because if the condition is yes, you go to the left. So that's why some other methods will post both sides X bigger than X, but that makes the picture very, very too much stuff on it. So I only put the condition on the left. So let me clean this up. Okay, so if X has some missing values, one split it will consider is the first one here that sends all the missing values to the left and all the non-missing values to the right, and we'll see how good is that, right? Then it will also consider splits like this, which is the same as the one above, right? But this one says go put the observations to the left if the variable is less than or equal to lowercase x, and x is not missing. So with this split, missing values will go to the right. Okay, so only observations that are non-missing and whose values are less than or equal to little x will go to the left. Otherwise, everything else goes to the right. Then when you say, well, what happens? Can you allow missing values to go to the left? Well, that's where this split is, right? This split says that if x is missing, or if x is not missing, then if x is less than or equal to little x, then you go to the left, right? So this would cover every possible situation. The asterisk here is an indicator that if you want, think of asterisk as missing. So the fact that it's in there and the inequality means missing values go to the left, right? So guide will search through all these possible splits and find the best split. All right. Now, sometimes you have multiple missing values, right? So for example, in our data earlier, we have a 0 and a -1, right? If you don't mind, let me go back to yeah. Right. So there are zeros and -1, right? 0 means it could be that it doesn't exist, so it's missing, but it makes no sense to impute it. Like spouse or farm wages, 24% of them are in this category, and you can impute it with 0, maybe okay, because if there's no spouse, how can you have any income from that spouse? But if it's a spouse's age, it wouldn't make sense to impute the spouse's age to be 0 just because there's no spouse, right? So the 0 is a special kind of missing. The -1 is sort of a refuse to answer kind of missing, and 15% of them did not answer, right? And they are possibly married farmers, but they did not give the answer here for how much the spouse earned in off-farm wages, salaries, and tips. So now we have 2 missing values. When I was visiting the Bureau of Labor Statistics, they have more than 2. I think they have 4 types of missing values. So this thing was actually partially developed while I was visiting the Bureau of Labor Statistics about 8 years or so ago to handle this situation. So what the Bureau of Labor Statistics does is that they don't use zeros and ones. If a variable is missing, then they're just coded with some missing value code, which I call NA. But then they have a missing value flag variable, which they conveniently put an underscore next to the name, and it's a letter, right? So the letter is C if it's a missing value that we need to impute, like somebody refuses to answer or somebody does not remember. This missing value flag will be an A if it's validly missing, like age of spouse when there is no spouse. And then it's a letter D if it's a valid response. That means it's correct and it's an observation, right? So in this case, we now have more possible splits. So we have 7 types now, right? The first split is to consider is put all missing values to the left, whether they are validly missing or they refuse to answer, whether it doesn't matter whether it's A or C. So basically, this condition is the same as x underscore equals to A or C, right? So x underscore is a missing value flag, right? So, okay. Then another possible split we'll check is whether the x underscore, the missing value flag is A. So if in this case, if x is age of spouse, this will say go to the left if there's no spouse. So it's equivalent to marital status, right? Sometimes if you know marital status, you can figure out this person is not married. Sometimes you don't have marital status, but you just have age of spouse and it's coded as validly missing. So that middle split would be one which sends all people with a validly missing age of spouse to the left. The third one would send every observation for which the missing value flag code is a C. Those are the people who refuse to answer this question. They go to the left. Then the fourth one is the usual x less than or equal to little x. And these two are actually sibling, these two are sibling splits, because one has an asterisk and one does not have an asterisk, right? The one with the asterisk, x less than or equal to asterisk x, means missing values go to the left, besides the condition x less than or equal to the x. The one without the asterisk says, basically puts the missing values to the right. Okay, and then there is this one, which is x less than or equal to x if x is not missing, or if x is missing but it's valid in missing, then you join them, right? So this is like combining this two with you know, like this, or rather I should put a plus sign, and this is combining that with C. So there are 5 types of splits that guide will check through to find which is the best. All right, and guide is the only regression tree algorithm existing which does this. So here's an example. Okay, so R1105 is amount of amount you spend on food for the farmer. Okay, so the first split is on R1106. R1106 is here. So we're trying to, so this is a regression tree where we try to impute the amount the farmer spent on food, and that farmer did not give a number. So we're going to impute it from the other variables in the data. The first split is R1106, which is the amount that the farmer spent on utilities and household supplies. So it says, top here, it says, if it's less than or equal to 3, you go to the left, and there's no asterisk under the inequality, which means missing values go to the right. Right? Okay, so remember those codes, they small numbers, 1 means 0, 2 means 0 to $500 and so forth. So less than or equal to 3 means that on the left branch, the people, the farmers that go to the left did not spend too much on food expenditure. Those that go to the right spend more. Then you come to here, the next one. All right, so among those people who satisfy the first condition, the second condition is R1118, is all other family living expenses, right? And it's less than or equal to 1 with an asterisk. Okay, so 1 actually means $0. Less than or equal to 1 for on the coded range means actually they're negative. I don't know how it can be that maybe they get negative expenses somehow, or probably just 0 or missing. So most I think most of the observations going down this branch have missing values in this variable. And then you come down to the third one, which is R1113, which is total farm sales last year. Right? So you can see here that this is a fairly complicated imputation method. There are a lot of imputation cells. Those are the terminal nodes. I should say I color them in 2 different colors. Yellow, every time you see a yellow and light blue imputation cells or terminal nodes, yellow means that the mean is above average. So there is some average value for R1105. And again, you have to remember that R1105 is a coded integer, right? But anyway, if you come down to this node, you have 2 numbers. One is in italics, that's a sample size. Okay, we have about 18,000, is it 18? Oh no. Yeah, 18,000 observations, 2,000 of them, 2,178 go to the right most node. And the second number at the bottom is the mean of the coded values, right? So of course, we are not going to use this tree to do the to impute the missing value with a 10.28 because 10.28 is not an integer. But we're going to use this node as an imputation class for hotdog. So anybody who is missing R1105 and happens to come down this branch, right? There will be 2,000 observations in here who have non-missing values on R1105, and we're going to randomly pick 1 from the 2,178 observations and impute it with that integer code. If the observation comes down here, so this is a person again without the R1105, there are only 379 farms in there. And we're going to impute them randomly by picking one of the 379 observations, right? So one thing I want to point out here, and that's why I highlighted many of these splits in red. Those variables in red, you see some variables that are not in red, right? You see marital status, and you see this variable not in red. These variables in red, they're actually components of that total expenditure. So remember, there's a variable called exp underscore tot, which is one of the variables that the ERS wants to impute. All these red variables that go in to try to impute R1105, they're themselves part of the components that make up the total exp underscore tot. So we are using, we're not, when we try to impute this component food expenditure R1105, we're not using variables that are irrelevant to this variable. There are all other kinds of expenditure, right? Like here, utilities and household supplies, out-of-pocket health and medical expenses, all other family expenses, fuel maintenance, repairs, insurance, parking, etc. for non-farm vehicles. So it's using as much relevant information as possible. Okay. So here's just one example of a regression tree. Here's a propensity score tree. And in the propensity score tree, remember, we're trying to estimate the probability that the variable is non-missing. So here, R1104, this variable is a component of expenses, total expenses, and actually means, this variable means the rent payments for the producer's dwelling. And now you can see splits like this, right? You can splits like the x-axis is R956, and if R956 is non-missing and less or equal to 9, or if R956 is missing, but its missing value flag is A, validly missing, then you go to the left, all right? And then at each node, again, the first number is the sample size. The second number now is the probability of Y non-missing. Remember, this is a propensity score. So it's like a logistic regression curve. Okay. So now if you use this substitute for the logistic regression propensity score method, we will impute by letting each observation fall into this tree, and these nodes are the imputation classes. So again, yellow means the propensity scores are higher. So you could see here it's 90%. And 90% of the observations in this imputations class are non-missing. There's 92, there's 90, 94, 94, 93, right? The blue ones have a lot more missing values. Only 10% of the observations in here are non-missing that variable 1104. Here there's 49%, right? So you can see the imputation classes are very explicit. We have 80 variables. It doesn't have to use all of them, and these are ones that picks. So now, okay, let's see what is the result. Okay, how good are we doing? So I use this method. So again, what I do is, this is just one of the components that may be missing. I impute all the components with all these trees, and then I add them up using the formula to sum the total. I convert the imputed interval codes to the midpoints of those interval ranges and then sum them up. And this is what ERS does with their own imputations. So this is ERS, right? This is our first variable, total off-farm income. TOT is total, OF is off-farm, I is income. Surprisingly, so this is regression tree, guide regression tree is propensity score tree. Surprisingly, we get 2. Actually, it could be more than 2, because sometimes if there's more than 1, I'm using R here to draw it. It just gets overprinted. It doesn't show how many are there, but there are at least 2 that are very negative. That means these are people whose total off-farm income, they actually have a loss, right? They actually have a loss. How come? You see, the way ERS does it, they are just taking the observed total off-farm incomes and imputing them with the observed off-farm incomes. So they never get outside the range of the observed total off-farm incomes. How come? Why is it that the regression tree methods can get you things outside the observed. That's because it is using, so like this one, this variable has 10 components. So we impute each component, all right? And if a person actually has, a farmer actually has a loss, some of the components may be very small or negative, and sometimes they are missing. So, but when we impute, if the other components like utilities and so forth are low, then that means that you are likely to see that food expenditures also low. So if there are two of them are components of total off-farm income, if one is low, you expect the other one to be low. But if one is low, but the other one is missing, well, the guide method would not impute a high value for that because it uses all the other variables. So you can have the 10 components, if 50% of them are missing, each of the missing components can be imputed as very low, very low, very low. And now when you add them up, you get outside the range of the observed total income, right? So this is expenditure, total expenditure, right? So you see the same thing, right? So there are a few here that the ERS method gives that very close to zero. But if you look at the three methods, there are many more that are very close to zero. Okay, and this is the non-farm assets, same story. So now I show you the weighted means and medians and standard deviations, right? So ERS is the current method. I highlight in red. All right. So for total off-farm incomes, ERS, the current method is estimating $81,000 for the median. If you look at the non-missing data, if you just look at those that are non-missing, a total off-farm income, the 50% of the data that are non-missing, the median is only 70,000. If you use guide, use a regression tree method, the median of this, so the median of this is actually the median of these box plots, right? So you can, it's hard to see here, but you scrutinize it. The median is the middle line, and this ERS is a little bit to the right of that middle line. Okay, so that's why we're seeing this. Okay. So if you use a propensity score tree for the total off-farm income, you get 72,000. So none of this is as large as what is being used in the current method. Similarly with total expenditure. Total expenditure, the median using the ERS method is 45,000, which is higher than the other three in this row. And non-farm assets, the current method is $826,000, which is more than double what the guide methods give, and also more than double what you get if you use complete case analysis, which is a non-missing. And then the standard deviations, you can see the standard deviations among the three, the current method underestimates standard deviation. And this is expected because you're using conditional means. So all the missing values are imputed with a constant, all right? Not the same constant, but they're like 15 constants because they have the age class and education class, 15 imputation cells, and you replace them with constants, and you underestimate the variance. Okay, so the current method overestimates the medians, sometimes by a lot, and underestimates the standard deviations. The means seem to be okay, right? That's because conditional means are okay if you underestimate means, but conditional means don't help you to estimate the medians properly. And these are correlations in case you're interested in. So this is so we are imputing three totals, right? The total off-farm income, expenses, and net non-farm assets. So if you use the ERS method, you get these numbers in red. If you use a complete case analysis, that means the only those observations where you observe all three totals, then you get those correlations. They're higher than the current ERS method. If you use the regression tree methods, they are lower. And this is not surprising because if you use conditional means, you tend to inflate the correlations, right? So So 3 models used for missing data. You can use them for conditional mean imputation if you use regression trees. If you use propensity score trees, I didn't talk about this, but there's another method called inverse probability weighting. The moment you have the propensity scores, you can use that IPW or inverse propensity score weighting to calculate the mean, right? Or you can use hot deck. Currently, I sort of like hot deck because hot deck tries to recover some of the overcome some of the underestimation of variance. Okay, now I want to, before I finish, I want to tell you about something very interesting about COVID data. So during the 3 years of COVID, I was involved in a very big study of 21 health systems across the United States. This was sponsored by the National Cancer Institute. So Wisconsin was a center where all this data were sent to. And what I tell you is only part of the data, the sort of initial part of the data. It already has 85,000 COVID patients, and about 18% of them actually died or were intubated, right? So one of the questions was, what are the variables that would be predictive of somebody dying from COVID-19 or getting intubated among those patients who were admitted to hospital, right? So there were 49 predictive variables. There are actually a lot more, but we use 49. There are demographics, sex, race, ethnicity, BMI, smoking status, blood type, and so forth, and comorbidities, asthma, COPD, diabetes, cardiovascular disease, chronic renal disease, and then medications that, whether they're taking blood thinners, steroids, and bronchodilators, and so forth, right? So what we want is to model this, try to estimate the probability of death or intubation using a regression tree. So here's a regression tree, right? So the regression, this may be a bit, let me see whether I can enlarge this. All right, I can enlarge. Right. So it says the first split is on age, which everybody knows, right? We all know by now that if you're older, you're more likely to have more serious consequences if you catch COVID. If you're younger, you will not be as likely. So the first split is on age, which is very reasonable. The second split is on smoking status, missing. This is smoking status, missing. At first, I didn't believe this, okay? Smoking status is a variable that is coded current smoker, former smoker, never smoker. And it's only coded as missing if the information is not in the electronic health records. So all this data were pulled out from all these very big hospital systems across the United States. And you get smoking status being missing. And what does that mean? Everybody has a smoking status. It's not like somebody doesn't have age of spouse because he's not married, right? Everybody has a smoking status. But it's the second most important split. And here, so if you remember, yellow terminal nodes, all these yellows, right, means that the death rate is higher, okay? The blues are the lower death rates, right? Or death or intubation. So the rates are at the bottom of each of these nodes. So you see that most of the yellows are on the right side of this first split, which you expect, right? Because these are older people, they're more likely to die or have to be intubated. If you're young, then you go to the left. And if you're young, nothing much happens very much because most younger people are healthier. So the tree over here is shorter, right? So, but you can see now if I clean this up a bit more, and we look at here, this part will be all those younger people, age less than or equal to 55, for whom we do not know the smoking status. This part for all the younger people, age less than or equal to 55, for which we know the smoking status, right? And it doesn't seem to matter what is a smoking status. As long as we know your smoking status, okay, you are less likely to die or be intubated. For example, here, you see, this is 49% probability that you die or be intubated. And 999 people in there. Over here, there are 2,698 people, and the probability of death or intubation is 18%. Whereas here, this is 11%, 19%, 4%, 10%. So you see that smoking status, if I don't know your smoking status, you are more likely to die or be intubated. If I know your smoking status, you're less likely to die or to be intubated. Now you think about that, you think it's kind of crazy. I mean, the same thing happens on the right side here. This is for the people above 55, right? So if I don't know your smoking status, the chance that you die, or even to 45% here, 35% here, 27% here. Whereas if I'm on the right side of this, I get 32, 27, 36, 20. It's less than what happens to people who, for whom we do not know the smoking status, right? So I was collaborating with doctors, and they say this doesn't make sense. And they say, can you try to impute smoking status first? So I went to impute smoking status and run it again, and smoking status disappeared as a predictor variable, right? So you can have all kinds of theories. One theory here is that who are the people for whom we do not know smoking status? They are probably people who are so sick that they cannot be interviewed by the nurse upon admission. They could hardly talk, could hardly breathe. So that information is not recorded. Besides, when you have COVID, at that time, nobody knows how to treat COVID. This may be the last question anybody will ask a patient. Are you a smoker or not? So in other words, missingness of smoking status is an indicator of severity of disease. We are trying to predict severity of disease here. We're trying to predict whether a person will die or be intubated. That's severity of disease. Now, there are many variables that are very excellent in predicting death or intubation. For example, do you have sepsis at the point of entry? Can you breathe at the time of entry? But we thought that that's silly. You're using severity of disease to predict severity of disease, right? So we did not include those variables. We include pre-existing conditions, comorbidities, demographics. And we thought smoking status is a pre-existing condition. But it turns out that this missingness becomes indicative of severity of disease. So this is where, sometimes it makes no sense to just routinely impute missing data, because the missingness itself can be highly informative, right? So here's another example in the same picture. I think I'm almost out of time. Look at the green nodes. What are the green nodes? RH factor. They're all NA. What is RH factor? RH factor is rhesus factor. Rhesus factor is binary, plus or minus. It's your blood type, plus or minus. You could be O negative, you can be O positive, A negative, A positive. So here, not knowing your rhesus factor is indicative of severity of disease. So for example, here, right? The left node here, we don't know the people's rhesus factor, the sign of blood type. Here we know. If we know, your chance of dying is 41%, dying or intubation. Whereas if we don't know your rhesus factor, it's only 18%. So now rhesus factor itself is now also, I think, is an indicator of severity of disease, because you will know the rhesus factor if you have the blood test. If you have not been given a blood test, you will not know whether you are O positive or O negative, right? So who are the people who are given the blood test? The people who are given the blood test are people who are probably more severely ill, right? So that's why it explains that if we know your rhesus factor, you're more likely to die or be intubated. Whereas if we don't know, right, that probably means that you're not so seriously ill, they didn't do a blood test on admission, right? So it makes no sense to try to impute RH factor or smoking status, right? RH factor is something that you're born with. All these are other variables that are at the time you're admitted. How can you use those variables, this information, years after you're born to predict something that you're born with? I mean, causally, it makes no sense, right? So I just thought this is a very interesting example to warn people not to routinely impute missing data. The problem is that if you impute, you don't even see this at all. If I imputed all the missing data on rhesus factor and smoking status, I will have a picture that has nothing to do with them, and you will not know. Of course, scientifically, you would think it makes no sense that smoking status is missing. But as a statistician, if you are doing prediction models, you want to be aware the information in missing data. Okay, I think I'm out of time. Katherine?
We are at 4:32.
Okay.
Yeah, do you have some time to take some questions?
Oh, sure. Yeah.
Okay, thank you. So first of all, I want to say, Wei-Yin, thank you so much for this presentation. It was really interesting, and thank you to everyone who attended. If you need to drop off, we understand the questions will be recorded, and you can also reach out to me, and I can put you in touch with Wei-Yin if you have any further questions. I've entered my email in the chat. There was a question from Caleb. Did you try gradient boosting, random forest, neural networks, or other machine learning algorithms besides regression trees for imputation?
Well, I'm not so familiar with all those algorithms, but I think the first question is, are those algorithms applicable when you have missing data, right? So the thing is that, you see, when you have missing data, if you have an algorithm that cannot handle missing data by itself, then you have to impute the missing data before you can, like logistic regression, right? So you cannot apply logistic regression until you impute everything. But imputation, so logistic regression or linear regression is the purpose is to predict something, right? Predict something about Y. But suppose you have missing data in X1, X2, and so forth. Now you have to impute X1, X2, and so forth to predict Y. But the imputation of X1 is a prediction for X1, right? So you imagine you start off thinking, oh, I'm going to predict death or intubation from COVID-19, right? Then that's a prediction problem, and it's already awfully hard, right? But now I say I have other variables that are missing. Now, before I can solve my prediction problem on Y, I have to solve the same kind of problem on X1, and then X2 and X3, right? So I know people use something called a sequential regression, like mice, multiple imputation. That's what they sequentially impute one column at a time, right? But there's no theory that will get you anywhere. Even the author of mice, he wrote a book, Van Buren, in his preface, he said there's no theory here at all. Okay, so you can imagine there are imputation errors that are carried over from column to column. So the answer to that question is I have not used them. Because if they cannot handle missing data, then it's very hard to say that they're good or bad, because whether they're good or bad depends on how you impute the missing data, right? It's not the algorithm alone. You're doing something else to pre-process the data. So yeah, I would love to see someone show me a gradient boosting thing that is interpretable and that can handle missing data and so forth. I mean, there are some regression tree methods that can handle missing data. So when you come to smoking status here, for example, right, they will never split on the smoking missing. What they do is they will find whether the current smokers should go to the left and everybody goes to the right, or former smokers, or current and former smokers go to the left, right? And then anybody whom we do not know, they flip a coin. Right? So you never see missingness appearing in the tree. Okay, the missing data do get into the tree, but they do a coin flip or they do something else to push them down. So you never see a split that says, if it's missing, go left. If it's not missing, go right. So even if that information is there, it will be missed.
Yeah, thank you. And I think for gradient boosting and random forest, the benefit is you would use trees, but yeah, I guess the question is it beneficial to run multiple trees, and what additional information do we get out of that?
Yeah. Oh, random forest, actually, if you're talking about the R package, it cannot handle missing data. The R package for random forest does have one function called NA rough fix. NA means missing, rough fix. Rough fix means it just imputes every column with missing values with a median. So it is, yeah, it's automatic. So you would say, oh yeah, it handles missing data if you just make this call. But is this the right way to impute? Just put them, impute the median. And so, but the lucky thing about random forest is you cannot see the result. Okay. So I like to tell my students, you go to a restaurant, you pay a high price, you think the food is great, you didn't see what they do in the kitchen.
Yeah, that's true. Thanks. I have a question for you, but in the meantime, while I'm asking my question, if there are other questions, feel free to put them in the chat or raise your hand. So my question has to do with the sample size. So you have pretty large sample sizes. Is there a certain sample size that you need for trees? And I think in particular for missing data, if you had too few missing values, would you be able to split on missingness?
Sure. I mean, like here, smoking status that we're looking at, smoking status is a categorical variable, right? So you could actually code smoking status as a missing code. You don't have to impute it. So that's not a problem. As far as sample size is concerned, really it depends on the signal to noise ratio. Okay. So I've applied regression trees to factorial designs with only 64 observations and 54, 64, maybe 5 variables, right? -1, +1, and you get the tree. So of course, those are highly controlled experiments where the sigma is small, right? So, but for survey data, usually sigma is quite big. But for survey data, usually have a big sample size anyway.
Okay. So yeah, I guess I was thinking if you had too few values, let's say you only had, I don't know, 5 missing values out of a data set with 10,000, which would be a very good situation to have, but would you be able to distinguish between the missing values if you don't have very much data on those?
Oh, probably not then. Yeah, because we would consider a split like, missing go left. And if you only have 5 observations out of 10,000, you see the algorithm has some defaults as the minimum node size, right? If you have 10,000 observations, it probably will default to at least 100 observations in each node. And if you have 5 with missing data, that split will be ignored because it doesn't pass the threshold of giving you a node with at least 100 observations.
Yeah, thanks. I guess that would also be a very good situation to have if we had that in any of our surveys.
Yeah.
Is this the tree? Are there certain packages you use in R, or is this something that you developed?
Oh yeah, I developed this.
This is guide.
This guide. Yeah, it's not written in R because when I first started to write it, there was no R, there was no Windows, there was no IBM PC. So I wrote it in Fortran. But it's an exe file. You don't have to use Fortran. So if you go to my website, you can download the exe files.
Okay, great. Any other questions for Wei-Yin? Okay. Wei-Yin, thank you so much again. This was really interesting, and we really appreciate your time. And thank you to everyone who attended today's seminar. It was recorded and it'll be posted on the WSS YouTube channel, and I posted the link for that in the chat. If you have any other suggestions for ideas, topics, presenters for future seminars, please let us know. And we'll make sure to advertise any upcoming seminars via email and also on the WSS website. So thank you for attending.
Thank you.